So what was the last topic we were discussing? Yesterday we discussed about RMS and average value, right? So now we'll discuss the next important topic. By the way, am I audible to people who are on there?
Yes, sir. Yes, sir.
So is there any doubt from yesterday's topic? You understood average value and RMS value, right? So average value is calculated for which cycle? Half cycle. RMS value is calculated for full cycle. What is the value of average EMF in terms of peak value? 0.637 times E naught is what is average value. What about RMS value? 0.707 or I naught by root 2. So 1 by root 2 times E naught or I naught is the same as 0.707 times E naught or I naught. Right? This is what we saw yesterday. The next important topic that we need to see is something called as phasors and phasor diagram. Okay, this is what we are going to see. Shall we get started? Right. So as I told you in the beginning of this chapter, what we are going to do is, if you have an alternating source in your hand, right? If you have an alternating source in your hand, then you will connect that alternating source across different kinds of passive elements such as resistors, capacitors, and inductors, and try to find out what kind of outputs are generated. Is that clear? Okay. So for that, there are different ways of approaching. One is pure mathematical. So if things are purely mathematical, then it becomes slightly complicated because you need to have grip of many mathematical tools, especially calculus and other parts you need to be good with to understand the differences. More than calculus, you need to be good with trigonometry. Okay. That is, you should be able to visualize trigonometry, which is slightly tough. So in order to reduce the complications, what they have done is, they have started representing. Okay, they found a method where certain parameters like EMF and current. If you start thinking about EMF and current, right? What is basically EMF? Is it a scalar quantity or a vector quantity? What kind of a physical quantity is it? EMF. EMF is scalar quantity because it is work done. What about current? It's a scalar quantity because it does not follow the vector laws of addition, right? But the method that they found is, you can take these two quantities and try to represent them in the form of vectors only for the sake of understanding. Okay, and those vectors are given a special name called phasors. Phasors. So they are called as phasors, and the diagram in which you represent these two physical quantities is what is called as phasor diagram. So to conclude the whole story, right, what we are going to do is, we are going to draw the input, that is EMF, and the output, that is the current. So for a given EMF across a passive element, what would be the output? If I have to conclude this chapter in one block diagram, right, I'll call it like this. You give input across a passive element, it will give you an output. So the input is EMF and the output is current. Both are in the form of alternating. Okay. So this is what happens. We are going to observe how these input and output values are related with the help of a diagram called as phasor diagram, where EMF and current, though they are not vector quantities, I'm stressing on this point, though they are not vector quantities, they are represented in the form of rotating vectors, and another tool called as projection is used to observe how these quantities are going to vary. So first, let's try to understand this. Then when I start explaining the applications of it, then you will get a clarity of why we are using it. Okay, as of now, I've given you a little bit of insight of how it is going to work, right? So if I have to give you a definition, of what a phasor is. Please write it. So definition of phasor, P-H-A-S-O-R. Definition of phasor is a rotating vector that represents sinusoidally varying quantity. It's written here. A rotating vector that represents sinusoidally varying quantity is called as a phasor. Okay. Okay. So since you are saying it is a rotating vector, we need to give a velocity, right? So these rotating vectors are imagined to rotate. So make a note. This vector, that is a phasor which we are trying to talk about, is imagined to rotate with angular velocity equal to the angular frequency of that quantity. Please make a note of it. The vector is imagined to rotate with an angular velocity equal to the angular frequency of that quantity. Okay. The next point is its length. Okay. The length of that vector represents the quantity, represents the amplitude of the quantity. Write it down. You first write down, then I'll explain. Its length represents the amplitude of the quantity. Its length represents the amplitude of the quantity, and its projection upon a fixed axis, gives the instantaneous value of that quantity. I repeat, its length represents the amplitude of the quantity, and its projection upon a fixed axis, gives the instantaneous value of that quantity. And the last point is the phase angle between the quantities. The phase, P-H-A-S-E. The phase angles between the quantities is shown as the phase angle between their phasors. I repeat, the phase angle between the two quantities is shown as the phase angle between the phasors. Okay. So let me explain it in detail first. Now listen. What does the first point tell you? Check your notes. Yes. So first of all, observe. When I say diagram, here I am using vectors, right? So vectors have a starting point. So that starting point is generally considered to be the origin. So when I draw an axis like this, it is a simple x and y axis. Okay, x has nothing like time or nothing, it represents nothing. It is simple x axis and a y axis. Okay. So this is x and this is y. Now listen to this. If I take an arrow mark like this, concentrate this is what is important. If I take an arrow mark like this, what is the second point telling you? The length of the vector. So I've drawn an arrow mark with a particular length. The length of the vector represents amplitude of whom? Amplitude of that physical quantity. So what are the two physical quantities we are concentrating upon? EMF and current. So we know that EMF is represented with the symbol E is equal to E naught sin omega t. So when I say amplitude of EMF, what will it represent? It is E naught. Okay. Now, what did I say phasors are? Phasors are rotating vectors. Vectors are basically directed line segments. In the sense, a ray with a length associated is what is called as a vector. Right? So if I take this and assume that it is revolving in the anti-clockwise direction. Did you understand what happened? Let's say it revolved in the anti-clockwise direction with an angular velocity omega. So that's what the first point told you. The rotating vector is assumed to revolve with an angular velocity equal to the angular frequency. Angular frequency of the wave is omega. Is that right? So it revolves, and in time t, it would have made an angle of omega t. Is that right? So I'm actually combining the first 2 points and explaining. I hope there is no confusion. So this rotating vector's length is how much? E naught. Now there is another important word used in the second point. The projection. The projection of what? The projection on the respective axis will give you the instantaneous value. So what I can do here is, from the endpoint, see, generally a projection means, projection happens between a line segment and a line. Okay, projection is actually a mathematical term. Suppose I have a line like this. Okay. If I call this line as x dash, and there is a line segment like this. Okay. From the endpoints of line segment, if you are able to draw perpendiculars, then you will get 2 foot of the perpendiculars, M and M dash, accepted. The distance between M and M dash, the distance between the foot of the perpendiculars drawn from the ends of the line segment is what is called as projection. So you learn about this in detail in a chapter named 3-dimensional geometry in your mathematics. So now you are able to understand what is projection. They didn't give exact this definition, they would have given you a formula. But you have to visualize what is projection. What is projection? The distance between the foot of the perpendiculars drawn from the ends of a line segment onto whom? Onto a line. So generally, this is what is projection. Projection basically means dropping perpendiculars. So this length is called as projection of this line segment L on L dash. So if that is the case, then with respect to this vector, with respect to the vector that I have considered, what do I mean by projection? It will not be length of the line segment. No, it will be a component of it. It will be the length of the line segment only if it is parallel to the line. It is bent like this. So if it is parallel like this, when you draw perpendiculars, it forms a rectangle. Then this length and this length will be equal. But here it is like this. It forms a trapezium. So this projection will not be equal to length of line. If you want me to clear the doubt, then the projection will be something like this. If you theta nirtha, it will be L cos theta. That is what the projection is. Right? In a similar way, if I try to drop the perpendiculars from the endpoints of the vector onto the axis, if you see one of the endpoints is coinciding with the axis itself, right? See, had it been like this, then I would have dropped a perpendicular from here and here, then this would have been the projection. But what is happening in this scenario? It is here. So what will happen? I will drop a projection from the endpoint itself. Is that point clear? So when I do this, I can drop 2 perpendiculars. So the distance between O and A gives the projection along y direction. The distance between O and B gives the projection along x direction. Okay. So if I call this as y, if I say this point is C, if I call BC as y, then what is y divided by E naught called as? y divided by E naught is what? Sine. Then y will be equal to E naught sine omega t. But what is E naught sine omega t? Is it not the instantaneous value of EMF? Now read that statement. Does it make sense? The projection from the projection of the phasor onto the coordinate axis gives you the instantaneous value. So this y is what I call it as E naught sine omega t. So this distance is also E naught sine omega t. Is it clear? It will be cos omega. It is also. You can see that is also E naught. So you can either, when they say sinusoidally, it can either be sine or cosine. But in our syllabus, we are taking only sine. There are books which will be dealing with cos also. It's exactly same as what you have learned in simple harmonic motion. Okay. Then this will be how much? E naught cos omega t. Am I clear this? Is it clear? So this is what happens. This is the phasor diagram only for one vector. Okay. I cannot call this as a complete phasor diagram because I have only input here. What else is needed? I need the output also. Okay. So for that, what I will do? First, copy this.
So can you scroll little up?
Is it okay?
Yes, sir.
Copy it.
Sir,
Tell me.
yesterday the last concept you are telling the significance, that should be the value of DC, the 0.70.
Yeah, RMS value.
RMS. So we can connect any device AC or DC, both.
To whom?
Any device, because that with that value I can replace AC with DC. No, sir.
Yeah, you can do that, but DC the problem is you cannot hold it for a long duration.
Okay, sir.
AC is comparatively easier to generate.
Okay, sir.
Is it clear?
Sir, O to B is it E0 cos omega t?
What do we represent?
No, sir, that O to B distance. It is cos of.
I'm not able to get you. Cos.
So, sir, from O to B, that distance you have written
That
cos
is
or
not
sine.
cos. Not cos omega t. Okay. Is it clear, guys? Right. So we'll see how to represent both on the same graph or in the same diagram. If this is E naught, for example, then I can think of another vector which is also revolving in the same anti-clockwise direction. But now I'll call this as, so if I say this angle is omega t, I'll say this angle is omega t plus phi. This angle is, I'll take it as omega t plus phi. Then what is this angle called as? Then how much will this angle be? There will be phi, right? So from the end of the first vector, if I drop, then this is called as E naught sine omega t. If I drop a perpendicular from here, then this will be called as I naught sine of, it will be omega t plus phi, because I need to write the corresponding angle it makes with the x-axis. So it is sine of omega t plus phi. But if you observe in both the cases, you can draw the phasor diagram only if both the input and output value have the same angular frequency. Means if this is omega and this is omega dash, you cannot draw the phasor diagram. That would be the next point we will see. Is this clear? So this whole set is what is called as a phasor diagram, where you are able to represent the input and the output along with the phase difference between them. Okay. So write it down.
Sir, is it E naught sine omega t plus phi or I naught sine omega t?
It is I naught sine omega t plus phi. This is E naught. This is I naught.
Okay, sir.
Yes. So the orange color one is I naught and the red color one is E. Is it clear? Which one? That's what I wrote. No? So this distance is E naught sine omega t. This one is I naught sine omega. One minute. Which one? See, the orange color length is I naught. No? The length of the vector represents magnitude or amplitude. Is that clear? So projections represent the instantaneous value. So this is what we are going to do throughout this chapter. We will be drawing the phasor diagrams to see how the input and the output are going to vary. Is it clear? Clear?
Sir,
Tell me.
sir,
Tell me.
sir, should both the vectors should be in the same quadrant or can it be different?
No, they can be in different quadrants also. That depends on what this phi is.
Okay, sir.
Yeah.
So instantaneous value represents the projection. So projections, the distance between two projections in y-axis is different from x-axis.
Yeah, they are different. They are different because see, I drew only y-axis here because we are dealing with sine. Had I started the equation with cos, I would have drawn only x projection. So in the previous example, I wanted to show you both. Otherwise, I showed you what is sine and what is cos. Because what is the first statement? Say rotating vector which represents sinusoidally varying functions. Sinusoidally, sine over here, it can be cos also. That is why I wanted to show that. But actually, this is the diagram we'll draw. You can ask me, can't I draw cos? Not necessary. If you are treating the alternating current to be in terms of cos, then you can draw it. Okay. So having this in mind, 1 minute. So now we'll see what is the definition of a phasor diagram. So basically a diagram that represents alternating current and voltage of, listen to this point, the same frequency. Okay, that is more important. Means in the phasor diagram, you need to ensure that E and I have the same value of omega. In the sense, if E is equal to E naught sine omega t, I cannot be I naught into sine of omega dash t plus phi. No, you cannot draw the phasor diagram for it. So for phasor diagram to be drawn, both the frequencies should be the same. So diagram that represents alternating current and voltage of the same frequency as rotating vectors, along with the proper phase angle between them. phase angle now, how much is the angle of separation between them? We do know that phi. That phi is called as the phase angle. Okay. Suppose the alternating EMF and current are taken to be the values I is equal to, sorry, E is equal to E naught sin omega t and I is equal to I naught sin omega t, where phi is the phase angle between E and I. Then to represent these quantities as phasors, we draw circles of radius E naught and I naught as shown. See, circles, or why are circles drawn? Because you can represent that to be the length. That's it. So there is another way also. It is not necessary that you need to draw the circle always. That is why it's touched on that point. Okay. But one clarity that you need to have in your mind is the length of each vector represents the amplitude. Never forget that. And the projections represent the instantaneous value. That point is more than sufficient for me to take you through the rest of the chapter. Okay. Now we are going to get to the main context. That is what will happen when you connect the alternate AC source, okay, across a resistor alone. So yesterday itself I told you AC source is represented with a circle and a sine wave inside it. Okay. It's not sine wave, just a wave. Right. So the instantaneous value, the EMF of this is E naught sine omega t, which is connected across a passive element named resistor. When you do this, if the current is I, then I will be equal to E divided by R, where this I is also instantaneous value. So this I can write it as E naught sine omega t divided by R. Can I do that? When I do this, observe E naught divided by R, I'll call it as I naught sine omega t. So the instantaneous value here becomes I naught sine omega t. In the sense, if you give an input EMF of E naught sine omega t, the output current that gets generated is also I naught sine omega t. Means they both have the same angle. Is it clear? From this expression, the important point that we can conclude is E and I have the same phase angle, right? Because E is also in omega t, I is also having omega t. So when you draw the phasor diagram for it, if this is E, okay, if this is for the EMF, which I'll call it as E naught sine omega t, then this can be called as I naught sine omega t. Okay. So this E means we can change the color if needed. So you're able to understand what is happening. So EMF and current have the same phase. So this kind of a situation is said to be where EMF and current are in phase. Means if EMF is increasing, current will also increase. If EMF attains maximum value, current will also attain maximum value simultaneously. This is clear, guys. Right. No? When you plot the graph for this, when you plot the graph for this scenario, so in the graph, what you will consider is time on the x-axis and instantaneous EMF and current on the y-axis. When you do this, let's say this is how the EMF is, where the equation of this graph is E naught sine omega t, and this peak value is called as E naught. So I hope there is no confusion. So in the graph, the distance between x-axis and the peak value is E naught, right? Whereas the phasor diagram, the distance between the origin to the peak value is actually E naught sine omega. You don't get confused between both. So here it is E naught. Then when you plot the graph for current, it is going to be something like this. Okay, it will be something like this, where this graph is called as I naught sine omega t. The meaning of this is when EMF is attaining maximum value, current will also attain maximum value simultaneously. So this is the meaning of being in phase. Am I clear with this? So this will be 0, pi by 2, pi, 3 pi by 2, 2 pi, 5 pi by 2, 3 pi. It keeps on going like this. Next point is, shall I proceed? Yeah. It will tell you how much, or what is the out of phase value. That angle is there, no, that is important. See, this is a simple scenario that both are in same phase. There will be scenarios where the angle between them will be 45 degrees. So 45 also the drawing graphically is difficult, but phasor diagram is easy. But yeah, to conclude the story, first is you should always write the derivation. If they ask you explain what happens when an AC source is connected across the resistor, then you should always start the derivation like this. Let's say the input EMF is E is equal to E naught sine omega t. So first you'll draw the circuit diagram, right? So this is the circuit diagram, the simplest circuit diagram. Then you will say, let's assume that the input value is E is equal to E naught sine omega t. I will be equal to E by R. Then E in the place of E will substitute E naught sine omega t, and E naught by R you will call it as I naught. So based on the input and the output values, you first need to draw the phasor diagram, then the graphical representation. After that, you will conclude saying that the phasor diagram and the graph says that the input, the EMF and the current, they both are in same phase. Okay. Sometimes how the questions will be asked in exam is, they'll just give you this phasor diagram and they'll say this corresponds to which passive element. So for which passive element we have the input and the output to be in the same phase? It is resistor. So you'll be able to conclude that only if you know what happens in the other two devices as well. So for that, we will proceed with the next one. Okay. So first I'll finish capacitor, then you can write down the inductor. So write it down. AC source connected across a capacitor. So AC source connected across a capacitor. So if I take the input value to be E naught sine omega t, okay, then let's say the current flowing through the capacitor is I. Now, due to this input value, what will be the charge stored in it? So Q is equal to C into E, because we know this Q is equal to CV, right? That is from the second chapter. So Q is the charge that is stored in the capacitor, C is the capacitance, and V stands for the voltage that is applied across it. So if I write Q is equal to C into E, can I write Q is equal to C into E naught sine omega t? So this I can call it as instantaneous charge. Can I? I'll call it as instantaneous charge. Then if I differentiate on both the sides, dq by dt gives you C times E naught into, what is derivative of sine omega t? Cos omega t into omega. You apply chain rule. So this will be equal to omega into C into E naught sine omega t. But what is dq by dt? This is I, the instantaneous. Yeah,
So should we see cos omega t?
sorry. Yeah. Okay, so omega C into E naught into cos omega t. Is that right? Now this I can write it as E naught divided by, can I bring this omega C down? If I bring it down, it will become 1 divided by omega C into, this will be cos of omega t. This is clear. So so omega C, I brought it down as 1 by omega C. Only then when it goes to the numerator, it becomes omega C. Now what I can do is, I can call this E naught divided by 1 by omega C as I naught, and 1 by omega C is called as XC. Okay. It's called as XC, where XC is called as capacitive reactance. Where XC is called as capacitive reactance. Okay. Is it clear? Coming back to the left hand side, I can write this as I is equal to I naught, but here I have cos. So when I have cos theta, I can write it as sine pi by 2 minus theta or sine of pi by 2 plus theta. So out of these two, which one should I choose? I'll write and show you. If I write it as sine of pi by 2 minus omega t, then the challenge that we are facing is we cannot draw the phasor diagram for it. Because for phasor diagram, what did I tell you? They both should have the same angular frequency. So if you see, the input angular frequency is omega, whereas the output's angular frequency is minus omega. So I need to ensure that it is a plus. For that, I should not write it as pi by 2 minus omega t. Rather, you should write the value only as pi by 2 plus omega t. When that is the case, I can rewrite this as I is equal to I naught into sine of omega t plus pi by 2. Is this point clear? From this, I are able to understand one important point. So in the previous case, E naught sin omega t and I naught sin omega t came. Means they both had the same phase angle. Whereas here, what is happening? One is sin omega t, the other is sin of omega t plus pi by 2. Means the current is actually leading. The current is leading the voltage by a value of pi by 2. Okay. So when I draw the phasor diagram for this, so E is how much? What is the input value you took? E naught sine omega t. And what is happening to the current? Current is becoming I naught sine of omega t plus pi by 2. This is right. So from here, if you drop a perpendicular, this height is I naught sine of omega t plus pi by 2. And from here, if you drop a perpendicular, then this height is E naught sine omega t. This is E naught and this is I naught. Is the point clear? This is clear, guys. Yes. Now, an important point to be noted here is current leads the voltage by pi by 2, or voltage lags the current by pi by 2. See, what is leading and lagging? It takes some time for you to understand. But as of now, write it down. Current leads the voltage by pi by 2, or voltage lags the current by pi by 2. Okay. Now, what we need to do is we need to draw the graph for it. Shall I proceed? Did you all copy this diagram? Draw it fast. So we'll see the graphical representation of it. So listen to this carefully. This is time, and here you will draw EMF and current on the same graph. Okay. If I say this is the EMF, E naught sine omega t, then what happens to the current? Current leads the voltage by pi by 2. So the meaning of leading as of now, in form of graphical representation, what I would say is, when EMF is least, current will be maximum. And when EMF is maximum, current will be least, because it is already ahead of EMF. So if you see the graphical representation, so this dotted line represents the graph for I naught sine of omega t plus pi by 2. Basically, it is a graph for cos. Is it not the case? That is a graph of cos. So that is what we got mathematically in cos omega t. Cos omega t, we wrote it as sine of omega t plus pi by 2. So if I join it, then this is how the shape is going to be. Is it right? Am I clear with this? So now you see, initially EMF is least, but current is maximum. So at pi by 2, EMF is maximum, current is least. So this will be 0, pi by 2, pi, 3 pi by 2, 2 pi, and it keeps on going. Am I clear with this? Yeah, clear or not? We will see. The last point in this topic is, I gave you something called as reactance. What is it? So I gave you something like this. No? Xc is equal to 1 by omega c. What did I call this as? This is called as capacitive reactance. The meaning of capacitive reactance is, it is something similar to resistance only, except the fact that you can say this is the value of opposition offered by a capacitor to the flow of AC, or it is opposition offered by a capacitor to the flow of current through it. Okay. So if you see this expression, can I write Xc is equal to 1 divided by, in the place of omega, can I write it as 2 pi into f? So this will become 2 pi f into c. Accepted? Am I right or wrong? So Xc is 1 by omega c. So Xc can also be written as 1 by 2 pi into f into c. Now concentrate, I'm going to tell you something important. For direct current, For direct current, what is the value of frequency? For direct current, what is the frequency? It is 0. Because direct current is not going to oscillate at all. It is going to have a fixed value. It's a straight line basically. Right? So when f is equal to 0, what can I say xc will be equal to? For DC means if you take a capacitor will never allow DC to pass through because it will offer infinite value of resistance. This is a very, very, very important topic point. Okay. This concludes saying that capacitor does not allow DC to pass through it. Is the point clear? Okay. So that is why if you recollect in the second chapter, right, when you connected a capacitor, what kind of a device was connected across a capacitor? Was it DC or AC? Second chapter. We connected DC. We connected a battery, a normal DC battery. But if you see the whole chapter, nowhere we would have discussed about the point of what is the current flowing through the capacitor. Because in the second chapter, we learned capacitor with the objective that it is a device which is used to store charge. We never spoke about current through it. So the point here is whenever you connect a DC source across a capacitor and you want to calculate the current, it will become an open circuit. In the sense, it will not allow current to flow through it at all. So generally, when you see, right, there will be some problems. It's very rarely asked. If at all I give something like this, right, where a resistor and capacitor are connected in series, and I'm asking you to calculate what is the current flowing through this device, what will the answer be? You can close your eyes and say it will be a 0 because resistor will allow, but capacitor will block. Because what kind of a source did you connect? You connected a DC source. So that is why an important point to be noted is capacitors will not allow DC to flow through it. They allow only AC to flow through it. Is that clear? Am I clear with this point? Okay. And we also saw that Xc is equal to 1 by 2 pi into F into C. So I have to remember that value 1 by omega C and 1 by 2 pi F into C. So when I plot the graph showing the variation of Xc as a function of frequency, then the graph will be something like this. So graph will be like this. Is it clear? So this is how an AC source works across resistors and a capacitor. The next topic that we are supposed to see is inductor, that we'll see in next class. After that, we will be seeing what happens when you have the combination of resistor, capacitor, resistor, inductor, and resistor, capacitor, inductor, all the three together. Okay, these are all the major topics of this chapter. Is it clear? You're able to understand how to draw a phasor diagram. You understood how to draw graphs. Derivation part is easy only. If you see the derivation for each thing, it will be only maximum 3 to 4 steps. Okay. So important thing is understanding phasor diagram and the graphical part. Clear? So revise it and come. The next class we will discuss about AC source connected across internet. Okay. This chapter is for that. This is the graph for variation of, write it down, variation of Xc. That is, Xc is what? Capacitor reactance as a function of F. F is what? Frequency. Clear? So that's it. Those are online, I hope they're clear.
Yes, sir.
Okay, we'll end up finish.
Thank you, sir.
Yeah.
Thank you, sir.